Hi, this is Peter with CalcBook, and today we're going to be looking at a concrete spread footing, and we're going to be doing this example in metric units. So we've previously done a spread footing design using US customary units, and now we'll be doing a similar spread footing design using metric units. So just as a quick refresher here, right, our spread footings can resist vertical, lateral, and overturning forces. And CalcBook will do two checks, stability checks, right? So we'll do bearing pressure, sliding, and overturning, and then our strength checks, one-way shear, two-way shear, also called punching shear, and then bending, right, for our flexural reinforcement. And this is for single-axis bending only. So if you have a biaxial bending, you can do it in both directions separately or just choose the critical case. Okay, so let's take a look at our problem statement. So we're going to be utilizing ACI 318-19M, right? So that's the metric version of the code. Pretty similar between the two, just some different factors here and there. The depth of our footing is 0.5 meters. Our depth of soil above the footing is 1 meter. Our pedestal dimensions is 0.45 meters square, so in both directions. The height of our pedestal is 1.3 meters, so it's sticking up above the soil a little bit. The length of our footing in each direction, so it's a square footing of 3 meters. We've got 25 millimeter diameter rebar spaced at 300 millimeters. And our strength of concrete, our F'(C), is 28 megapascals, normal weight concrete, and our steel strength is 500 megapascals. Our allowable soil pressure load is 140 kilopascals kPa, and that's for dead plus live. And then we are allowed a 1/3 increase for wind and seismic loading. So our demands in the lower right corner there, we have a vertical dead load of 750 kilonewtons, a vertical live load of 500 kilonewtons, a lateral load due to earthquake of 100 kilonewtons, and then an overturning force of 400 kilonewton meters. And just as a reminder, that lateral load is applied at the top of the pedestal, so we'll have an additional moment due to the height of the pedestal to the bottom of the footing where the overturning occurs. So let's go ahead and open up CalcBook, and we'll get started on the design. All right, we've got CalcBook open now, so we can go ahead and click into our concrete design module, click on standalone design, and then our spread footing. And we'll go ahead and make sure we select metric here and then click continue. All right, now that we've got that loaded up, we can go ahead and start to make our selections here on the input pane. We'll go ahead and include the footing and pedestal weight. We want to include our soil weight. We do want to check sliding, so we'll toggle that over to yes. And then we do want to check overturning, so we'll also toggle that over to yes. Our lateral loads are due to seismic, so we'll leave that there as yes. That just has to do with the lateral bearing pressure that's used. The problem statement didn't say, no, it did say we're using friction coefficient, so we'll leave that as friction. And then we are going to include the top foot of soil for our lateral pressure resistance. That just has to do with the type of soil and the geotechnical recommendation and sort of what constraints you have of either if you have a concrete slab or pavement or whatever allows you to use this top foot or not. Okay, so let's go ahead and enter in our footing dimensions. So our footing dimensions here, we have 3 meters square, so it's 3 meters long, 3 meters wide. It is 0.5 meters thick, and then it has 1 meter of soil above it. Our pedestal dimensions is 0.5 square meters, so 0.45 meters long, 0.45 meters wide. Our height is going to be 1.3 meters, so it sticks up above the soil. We do not have any eccentricity in this problem. We'll do another metric example with eccentricity. Our rebar diameter, we're going to start off with 25 millimeters and see if that's enough. And then our number of bars, right, we're spaced at 300 millimeters and we have a 3 meters, so that's going to be 11 bars. And we'll get that going. And then the last thing we need to update is our bearing pressure. So our allowable dead plus live is 140 kPa. And then we get a 1/3 increase. It's giving us a warning here, just telling us that our total needs to be more than our dead plus live. So we are going to have that 1/3 increase of 187 kPa. And then everything else, I think, can stay the same. We've got our concrete strength of 28 MPa and then our 500 for MPa for our steel yield strength. So everything else here can stay the same. And then we can go ahead and add our demands. So click over to demands. We're going to use the ASC 716 load combinations. We have, let's see here, Our axial demand dead load of 750 kilonewtons. We have a live load of 500 kilonewtons. And then we have a shear demand due to earthquake of 100 kilonewtons. And then we have a moment due to earthquake of 400 kilonewton meters. So we are all set up in our inputs here. We've got everything set that we need to. We can already see quickly here that we are over capacity for our bearing pressure dead plus live. So we'll adjust that when we get to that calculation. We might have to do some sort of fine tuning of this foundation to make it work. So let's go and start stepping through the calculation here. Right, we've got our supplement loading. This is just our additional dead load weights that we've calculated. So our footing weight, our pedestal weight, and our soil weight, that all adds up to our total dead load. And then these drop downs here identify the critical load combinations for each failure mode that we're going to check. So we have our ASD level dead plus live, our ASD level overturning, that's for our bearing pressures and overturning, and then our sliding as well. So that's going to be our ASD level loading for seismic or wind for our lateral loading. And then we have similar ones for our strength checks. So we have a controlling load combination for each different check that we look at. So let's go ahead and look at our bearing demand here, right? This is where we have an issue. So if you look at our dead plus live bearing demand, right, we should not have any eccentricity since we don't have any moment, which we do not, so no eccentricity here. And so it's just that our bearing pressure is too high. So the easiest way to take care of that would be just to increase the size of the footing. So why don't we go ahead and make this 3.5 meters by 3.5 meters and see if that takes care of it. So it looks like that did take care of the bearing pressure, but now we've jumped over to a two-way shear capacity issue. And the easiest way to increase or to take care of that would be to increase the thickness. So we can try 0.75 meters, see if that works. That's a DC of 1. And that's going back to bearing pressure. So that's okay. And then we're getting a warning here, and I think it's going to be because of the reinforcement. So we increased the size of the footing, but we did not update our flexural reinforcement, so we need to go update that. So we increased it. We can maybe go up to 13 bars and see if that works. And that seems to take care of it. So just 13 bars, just adding some bars there because of the increased width and size of the foundation. So looks like that has taken care of our issues, and now we're at a DC of 1. So it's a perfectly economical design. And then we can step through the rest of the calculations here. So look at our seismic and wind bearing pressure, which does not control, but this one does have eccentricity, and so we do have some overturning pressure, right? So we get a different distribution of our bearing pressure diagram. So we have 173 kPa, but remember this is actually compared, even though this is more than our demand for dead plus live, it's compared against the 187 kPa capacity because we get that 1/3 increase. So the critical DC ratio is for dead plus live. And then we recalculate our bearing pressure using our strength level load combinations to get our bending demands. So we go back through using our LRFD load combinations. We calculate what the bearing pressure is on the left and right, and then also at the face of the pedestal. Then that gives us the the bending demand left and right of the pedestal based on sort of this diagram here. We have our rectangular bearing distribution plus the triangular portion and their respective moment arms on each side, and that gives us the bending demand on each side of the pedestal. So we get a total bending demand of 892 kilonewton meters. We want to calculate our one-way shear and two-way shear, right? And we'll kind of skip some of this stuff. We've looked at it before in our customary units. We have a maximum one-way shear of 665 kilonewtons. And then we have a two-way shear demand of just over 2,000 kilonewtons. So then we go to the capacity side. Check a look at our sliding capacity, right? We are using that top foot, so our sliding resistance diagram looks like this of our lateral bearing pressure, right? We can calculate the pressure at the top and the bottom of the footing and use that for our lateral bearing pressure. And then we add in our friction bearing pressure, our friction sliding resistance. We add those two together, we get 330 kilonewtons of resistance for sliding, and we have a pretty decent factor of safety there, 4.7 against sliding, so that's good. Go to our overturning capacity. and we calculate our overturning moment again, and then we compare that against our resisting moment, right? So our dead load multiplied by half the width of the footing, and that gives us a factor of safety of 3, so we're acceptable there. We'll take a look at our flexural capacity, and we're not going to step through every calculation here. This is just a typical concrete beam section analysis, right? So we're just looking at the reinforcing, checking our minimum steel, our phi factor, that sort of thing, and then calculating our moment capacity of about 1,800 kilonewton meters. We check our one-way shear capacity, right? Which is just going to be the concrete strength of almost 1,600 kilonewtons, and then our two-way shear capacity, right, which has a few more checks, and we've got to calculate the perimeter, the critical perimeter there of punching shear, and then we get 3 different capacities, take the minimum of that, and we get about 3,900 kilonewtons. So again, our controlling failure mode is bearing pressure. We have a D/C ratio of 1.0, so we're okay. And that is a footing design in CalcBook utilizing metric units. We hope you enjoyed the video. If you have ideas for other videos or other questions or comments, please let us know in the comments below. We hope you enjoyed this one, and we'll see you next time.